Thanks everyone. So I'm Bastien. I work at Movement by Toyota on a software platform for vehicles called Arena. I'm originally a mechanical engineer turned into a computer scientist. My expertise is in compilers, operating systems, security, hardware, and programming languages. I shared the evolution of the C++ programming language through ISO's standard computing. 皆さん、はじめまして。私は JS です。本日はこのような機会をいただき、ありがとうございます。これから英語で練習をします。Let me adjust my clicker. So today, I want to convince you that we don't engineer software, but we craft it. And we believe that we perform engineering, we really try, honestly. But by and large, we don't achieve engineering. Our industry's desire to adopt software engineering and software-defined vehicles, I believe, is hampered by the gap between software craft and software engineering. Okay, so I'm not saying that software craft is undesirable. In fact, I see this talk as really a love letter to well-crafted software. So I love crafting good software. There's really beauty in well-crafted software. However, my enjoyment and the software's beauty are not relevant to the people that are most important to vehicles. So those are the passengers and the driver. So I also believe that some software is engineered in some products, but I don't think that's the majority. And I'm going to try to cover that today. So let's try to contextualize what I'm trying to get to with a bit of a timeline based on this quote here. So I have a timeline for software development here, and I have to do three timelines. One of them for programming languages, one of them for software development, the first time I'll show you, and then the last one for automotive standards. So let's look at them. So here, in the early 50s, we have the term software engineering came about. That term was popularized by Margaret Hamilton when she worked at MIT leading the development of some of the software for the Apollo program at NASA. This is really when we started seeing the term software engineering come up in roughly 1960s, mid-60s. Then we have, the first software engineering conference in 1968 was created. And that was very, very much an aspirational thing, right? People decided that they wanted to do engineering, and they created the first conference for software engineering without really having an understanding between them of what software engineering was. This was a fairly big event back then. There's a lot of fascinating writing and look-back papers that were written afterwards to try to explain at the time what people thought they were doing well, not so well, and why they wanted to do engineering. Afterwards, we had the first international conference on software engineering here. So this one is specifically on software engineering. Then we have the Software Engineering Institute at Carnegie Mellon University, a fairly well-known institute. We have the book on design patterns created here. We have Unified Markup Language. We have the Agile Manifesto. The SWIPOC, the Software Engineering Book of Knowledge. We have DevOps that was created, SAFe, the Scaled Agile Framework, and then 50 years of software engineering. There's a celebration in the IEEE that celebrated 50 years of software engineering. It has really, well, bad software engineering. It has really fascinating content if you go back and read that content from IEEE. There we go. Try to turn it off and on again. It's predicting my joke from later if I say turn it off and on again. There we go. So let's start back. Running through history really quickly. Hopefully I turn it off again. I swear this is not scripted. I was not trying to make a software engineering joke by having software not function for me. Okay, so let's look at programming languages. I think programming languages are a tool that we use to create software, and I think it's important to contextualize how these tools were created over time and how they've evolved to help us create software. And I would say that you could argue there were programming languages before 1957, but I would say that Fortran is the real first programming language. You could use assembly before, but Fortran was a high-level language that had an optimizer, it was the first one to do this, to try to help you write high-level programs and then map it properly onto hardware. I programmed in Fortran professionally, and I actually think it's a really good language. For being the first real programming language, it's a wonderful language. I think it does a lot of things well. Abstraction is not one of them. Right? So as a tool, it's a very good tool. For a mechanical engineer, very good, but it very much does exactly what you said. Right? So it's a great tool. There's a variety of other tools that got created. Lisp was created shortly after Fortran. COBOL, still in action today, BASIC. We have C, right? Everyone knows C. Smalltalk. So Smalltalk was the first real attempt, or popular attempt, at doing object-oriented programming. Fascinating language as well. And Smalltalk, bringing object-oriented languages to people's consciousness, was trying to create abstractions on top of software to help developers create better software. Then we have Ada, which was used mostly in safety-related industries. We have C++, 1985. We have Perl. I'm not going to talk about Perl. We have Python, which is very popular. Then we have Java here, right? So Java really ran the concept of object-oriented programming and abstractions. And the same year, JavaScript came out as well. Completely different language, shares a word, but completely different. I would say JavaScript is the second most popular language in the world. The first most popular programming language in the world would be Excel. Right? So everyone knows how to use Excel. They don't realize that they're programming when they're using Excel. They are. The second most popular language in the world is JavaScript. And then there's a big gap of, I think, relevant languages to my discussion, but I'll put Swift and Rust in here. I think Swift and Rust are two of the most interesting programming languages that have significant abstractions. They've learned a lot from the evolution of programming languages over the last since 1957. And they're both very low-level languages that offer powerful abstractions, but map very efficiently to low-level hardware. So I think those are the two kind of more interesting programming languages that have come out in a while. Okay, and let's look at automotive. So I'll try to simplify a bit the picture from automotive, but I think automotive really started trying to do software engineering when things like Misra started to happen. Right? Before people were working individually, but I think Misra in 1998, I believe, is the first real attempt at doing automotive software engineering through standards and shared values. So there's then IEC 61508. I can never remember exactly what it means, but so I'll write it out. Functional safety of electrical, electronic, programmable, electronic safety-related systems. Whew, that's a handful. Okay, then we have RSR, right? That's good. Then we have ASPICE coming out. We have ISO 26262, which all of you are very familiar with, right? So road vehicle functional safety, much easier to say than 61508. Then we have this AJ3061. So this one focuses specifically on cybersecurity guidebook for cyber physical vehicle security or systems. Then ISO 21448, that one is road vehicle safety for the intended functionality. I think that's a very important one. And then finally, I'll put this one here, 21434, road vehicle cybersecurity engineering. So if you look at this timeline, you've all witnessed key moments in the history that I've laid out here. Right? The field that we work in, software engineering, that's it. That's all of it. Some of you in the room were alive at the beginning of the history of our field. Right? It's a very young field. Right? You've probably all known or worked with people who had significant impact in key parts of this. This is very rare for engineering fields. Right? There's very few engineering fields where you can say, I knew I said once. Like, that's not a thing, right? Whereas in software engineering, all these things have happened in a lifetime, basically. So it's still a very young field that we're trying to understand. And I'll try to make a case on it. All right. So at the time, people in the first software engineering conference thought it was important to create legitimacy for software engineering. The term software engineering was aspirational. And there was a perception back then that software was in a crisis, right? That's not from me, that's what they portrayed when they created that conference in 1968. And there's extensive writing about this topic. So the term was aspirational. They did not see them as engineers yet, but they wanted to be engineers. Right? It was meant to be provocative, explicitly. They were saying, we want to engineer software. Okay, so what did they mean back then? Well, I'll give you a very long quote, and I'll just read it, because it's, I think, a really good quote about the software crisis, written in 1972. So the major cause is that the machines have become several orders of magnitude more powerful. To put it quite bluntly, as long as there were no machines, programming was no problem at all. When we had few weak computers, programming became a mild problem, and now we have gigantic computers. Programming has become an equally gigantic problem. In this sense, the electronic industry has not solved a single problem, it has only created them. It has created the problem of using its product. So this is an actually important quote. If you're not familiar, Dijkstra is a Turing Award winner. This is from 1972. He gave a speech to accept the Turing Award called The Humble Programmer. The Turing Award is the equivalent of the Nobel Prize in computer science. Right? So this is one of the pioneers in computer science and software engineering. His entire speech is about being a humble programmer. It's a really good speech. I recommend reading it. And so this award lecture came 4 years after the delivery of the software engineering conference, right? The first conference on software engineering. So everyone explained there was a problem, there was extensive writing, and 4 years later, guys came back and said, this is the topic of our age. Right? He took the opportunity of giving this speech at the software, at the ACM to accept his Turing. Right? And his point is, bigger computers are harder to program. And I think this is still true today. Right? The move towards bigger centralized ECU, that's the same thing. The same type of problem we have. You move from microcontrollers to big ECUs, you have the same type of problem. And Dijkstra really is a giant in the field, receiving this Turing Award. And what's interesting is, this is the most famous part of the speech, but if you read a few paragraphs later in the speech, he also predicts, so this is like a luminary in his field, right? Giant in his field. And his prediction in his acceptance speech is that programming will be much more powerful and virtually bug-free before the end of the 1970s, right? So that's not like just a random person saying this. This is a giant in the field, acceptance of the highest honor in the entire field, and he thinks that 8 years from that speech, by the end of the 70s, there will be almost no bugs in software. Right? So I think we've had significant optimism in the field, and I don't think software is bug-free today. And so why is that? Well, is there even a crisis? Right? What were the concerns that people had in 1968 to create a conference on software engineering and then declaring there's a crisis? Some people didn't like the term crisis. They said there was a software gap instead. But really, like, when you go through the reports of what people discussed back then, they identified a few things, and I'll walk you through them. They really had 7 concerns when they talked about software engineering being in a crisis. Concern number 1 here was that scheduling for software was just unrealistic. Right? It didn't make sense the way people plan software. I swear this is not scripted. Let's try to turn it on and on again. There we go. There we go. Thank you. So concern number 2, people perceived that there was a mismatch between ambition and achievements. People promised a lot of things and delivered fewer of those things. Concern number 3, mixing research, development, and production, which is a common concern. Number 4, economic pressures. There was a lot of pressure to deliver a lot of software at lower cost. Number 5, lack of programming experience. Number 6, systems are becoming more complex. And think back, this is 1968. Right? Think of your systems, whether they're complex or not, and tell me whether they're more complex than 1968 kind of systems. And finally, the concern that comes out, technological and methodological gaps. Now, this one is not very well explained because back then, people didn't have the words needed, the understanding to really figure out what does that mean to have gaps in technology and understanding. I think later on, people thought about design patterns or object-oriented programming as solutions to these gaps. But I want you to look at these 7 concerns and try to consider, are they valid today? Now, given that, they also didn't just list concerns, they also listed solutions in their reports. And those solutions are from 1968 in that context, which was still a new field. So keep that in mind when you look at them. Solution number 1, they really thought that simulation was one of the big solutions for the problems we have in software engineering. So simulation, so running software in a virtualized environment. So being able to execute a piece of software on another piece of software running on hardware. Another one, testing. Right? Testing was a really big important factor that they thought they needed more of. Then education and training was also quite lacking back then. And documentation and standards. Now, this was at the very beginning of the concept of software engineering, and these were the solutions offered. And I think those solutions are still valid today, right? So, have we really been in a 56-year crisis? I don't think that makes sense. I don't think I can say we've been in a software crisis for 56 years. The concerns listed and the solutions still exist today. Solutions are still valid, but they have different causes. Like the same concerns, different causes today. But they're roughly of the same shape. And are we then in a software crisis? I don't think so. I think we've really been coping with software for 56 years is what it is. And I don't want to be alarmist, but nowadays AI is the next kind of problem or solution that's coming along with software to try to help us change how we do software. Whether it's a problem or a solution, I'm not quite sure. So I would, instead of saying we've been in a crisis for 56 years, I'd like to say we've been coping with software for 56 years. All right. Okay, so let's step back. In the late 60s, the aspiration towards software engineering was based on a perceived set of problems, and they had concrete solutions in mind. But what is it that is an engineer in that context? What does that mean? What would they aspire towards? What's the term engineer? What does it mean? So I'll offer you a few examples. There's a lot of professional organizations around the world that unite engineers. Some of them are mandated by law. So I'm Canadian. If you want to call yourself an engineer or ingénieur in French, you have to be a certified professional. Just the same as a medical doctor or something like that. You cannot call yourself an engineer in Canada unless you're actually accredited through the right order. Similar things exist in other countries. And there's also professional organizations, like in the US, where it's not a mandate by law, but they still have their own definition of what engineering is. And if you look through all these definitions, they're usually listed through 3 requirements. Requirement number 1 is that you have to have applied expertise. So what that means is you have to have specialized expertise, a technical field. It's a learned calling, and you have to have continuous competence. So you have to continuously train and improve to be a good engineer. Requirement number 2 usually is that it has to be regulated in some form, not necessarily from the law, but it has to have an organization and regulations around it. And the key point is often that engineers self-regulate. It's not that the government tells you how to be regulated, it's engineers decide this is the right way to be regulated. And the way this makes sense is because the third requirement is around ethics. So usually engineering has a code of ethics, and the highest obligation for most engineering definitions is towards society, not towards a company, not towards your own personal achievements or anything like that. Being an engineer is a commitment to public service. So I would summarize the definitions of engineering as something like engineers offer products or services to the public while uploading their safety. And engineers hold each other accountable. Engineers help each other grow. Right? Now, if you look at my definition, nowhere do I talk about math, nowhere do I talk about design patterns, nowhere do I talk about how to do science of vibrations, aerodynamics. That definition would apply equally well to any profession. Right? A doctor could be described the same way I just described engineering. So I think that's an important point to internalize. When people in the 1960s were aspiring for software engineering, they were looking at having this higher calling. So I'll show you a picture to illustrate here. You'll agree that well-established engineering practices, such as mechanical or civil engineering, embody the requirements I've described. This is a picture from Apollo 8, NASA's Apollo 8 mission, this is the famous picture of the Earthrise. But even during Apollo's mission, software practitioners had applied expertise, right? You don't get to do that without some amount of expertise. And they really had high ethics. But surely, like, out of the three things I listed, regulations wasn't the sole thing that software engineers were looking at and saying, we really need regulations. I don't think that's what they were vying for. So I'm sure that each of you see yourself as an applied expert. You want to follow regulations and you're bound by ethics, right? And I think the key takeaway here is when you engineer, you really engineer for humanity, for people, right? To be able to do stuff like this. So if we look back, Margaret Hamilton, who coined the term software engineering when she was working at MIT with NASA on the Apollo project, she described her terms of her use of the term software engineering like this. This was her description of software engineering. Right? When she was looking back, I think it's from her lecture, the 50-year anniversary lecture that was hosted by Lee. She gave a talk, it's on YouTube. So she said, it was an ongoing joke for a long time. They liked to kid me about my radical ideas. Back then, when she started using the term, it was a radical idea to say that software engineering should be something. Okay, so let's look elsewhere. The term engineering is derived from Latin, ingenium, and it means ingeniousness or cleverness. Does anyone associate with cleverness when they do engineering? I mean, sometimes, but that's not really the purpose of engineering. So I don't think that's what engineering is all about. So I love clever code. It's fun to write. I really like writing clever algorithms, clever data structures. But cleverness is really not what we're trying to do in engineering. In fact, I think cleverness is what a craftsperson would do, not what an engineer would do. Okay, so let's look somewhere else. This is another definition. Software engineering is programming for those who can't. Again, this is from Dijkstra. He's a bit flippant when he says that. But you know, it's an interesting definition, right? Is software engineering just what people do who can't program? I don't know. Maybe I'm clever by quoting Dijkstra, but that's about it. Okay, so another definition, there's a book by Google, by a bunch of Google people, Type Splinters and others, called Software Engineering at Google. It defines software engineering like this. It says that software engineering is programming integrated over time. Now, that sounds compelling. It's kind of like got a math vibe to it. It sounds interesting. I don't think it really makes sense. It's clever. I think it's clever. But I think programming integrated over time would be technical debt, not engineering. Okay, so let's look at another definition. So what's an engineer? What is it? Well, I really see two considerations when we talk about engineering. I think that first of all, we got to consider surface versus depth, right? So engineering, software engineering, as we see, is a young field, right? So software engineering is developed by experts, and they have know-how developed over time. And this seems to be, this surface versus depth, seems to be what folks were really vying for. They were looking to be able to have depth when they create engineering. Let's turn it off again. Okay, so they were looking for depth, not just surface, when they declared what they call the software crisis. They wanted more depth. And I think the second criteria is intent versus outcome. Right? So desiring expertise, desiring to follow regulations, aspiring to having ethical behavior does not make it so. Right? Saying I want to behave ethically does not mean that I do behave ethically. That's very important. And so I think the experience of the consumer, right, the end result of the product that we create is what matters. If you try to engineer software in your little world and it has an unforeseen impact on consumers, on real people, on humans, that's the real outcome. It doesn't really matter if you try really hard. Right? Trying hard is really important, but the outcome is really what matters. And I think that's a key aspect of engineering. Okay, so I think the former consideration affects the latter. How often do you get angry at software? I mean, we've been having software issues so far, right? Can we just say, honestly, software doesn't really work so well. As humans, as a society, I assume you're all technical experts, but even non-technical experts know that software is not particularly good. We've accepted that software just kind of fails sometimes, all the time. Right? So that's a joke. Just turn it off and on again. And I swear this was not scripted. I wasn't trying to make it fail all the time. But what does it say of society that this is a common joke? Right? Software, you just turn it off and on again and it works. That doesn't seem really good. It doesn't seem normal to be a thing that we just, it's a good joke, but it's not totally compelling. And I think really what I want us to really internalize is we have to look towards the consumer as the person we're trying to help. Look at other humans for whom we write the final product. None of the definitions I've offered you so far really focus on the end consumer. So although engineering is usually described as having society as its highest obligations, I think we don't really consider this obligation most of the time to create software. Right? So it's no wonder we get frustrated in software. And this, to me, the outcome, the impact on humans, on the consumer, is the most important characteristic of engineering, the effect on people. And if you, in Japanese, it's ryosha sama, right? But that's the important aspect. You really must respect the customer that you are working with. Okay, so compare software's quality to other engineering practices. So we're in Tokyo right now, for those online. This is in Tokyo. It's the biggest metropolis in the world. It's slightly prone to earthquakes. Like there's earthquakes fairly often here. Really big earthquakes. So this is a picture of Tokyo from the Nihonbashi office, the 18th floor where Movement by Toyota is. And great picture. You see a lot of buildings. The only time I think of civil engineering failures is when I compare it to software engineering. It's not that civil engineering doesn't fail. They've had really good failures, but they've done a lot of work to mitigate those types of failures in the future. You would not be on the 18th floor of a building in a very earthquake-prone place like Tokyo if you didn't believe that civil engineers really knew what they were doing. And when failures had occurred, they had put significant work into their engineering practice to be able to prevent future failures. Right? And further on, when you think about turning off and on again, when's the last time anyone here has gotten frustrated at a building? Right? Like, you're like, this door, I really can't this door. Or like, the window, this window, it's terrible. This ceiling, I don't like the ceiling. That doesn't happen, right? Civil engineer has its stuff together. But we say turn it off and on again because we're frustrated in software. We've just internalized as humans that software does not work very well. Right? So when I say other engineering practices look back at failures and act upon them, compare how software practitioners react when issues crop up in software versus how the other engineering practices react. Right? And it's not that other engineering practices in the field don't make mistakes that affect society. But when they do, they take issues seriously. If you look back at the history of famous software engineering failures, there's things like Therac radiation treatment, right? That was caused by a race condition. We still have race conditions today. That was tens of years ago. There's still issues like the Mars lander that crashed because of unit mismatch. Unit mismatches are still common today. If you look at serious, big software failures, those issues have not been resolved. And that's not specific to automotive, it's just the truth about software in general. Okay, so the perception then is that software development doesn't produce quality outcome at the level of engineering. Right? We really try. I don't want to say that we don't try to have these outcomes, but we don't succeed in general as software practitioners. Why is that? Is it because it's a young field? I mean, yes, software is young, it's immature. Some of us have lived through the whole history of software engineering, but it's had a lot of years to mature. Right? So it still has to mature a lot more. Right? Let's not delude ourselves. But I don't think age of software engineering as a practice is the main thing holding us back anymore. I think we've made significant progress over the last 56 years to try to be software engineers. What is it? Well, I have something that I think defines why software is still quite kind of immature. I think the main issue shackling software engineering today is that we've not fully embraced the constraints on software. What do I mean by that? Well, when you think of physical systems like civil engineering or mechanical engineering, the main thing that constrains them is physics. Right? At their core, other engineering practices eventually hit a constraint that can't be overcome. Physics. You can't overcome the laws of physics, I think. The laws of physics usually guide how most engineers can solve problems. So that's not true for software engineering. Physical constraints on the resource available to a computer, the scale of the problem, the solution, but not the means of the solution for software creation. So in software engineering, it's mathematics usually that are the hard constraints on engineering. I think that's a fundamental observation, that other engineering fields are constrained by physics, and we doing software are usually constrained by math and nothing else. So put another way, it's extremely rare that a software engineer has to think of the speed of light, that they say, oh, this software can't do what I want it to do because speed of light. So far what I've been saying here is pretty abstract, so let me get a bit more concrete. Okay, so we have ISO 25010, which describes quality attributes, which you might think of as non-functional requirements. So those, this whole list that ISO 25010 creates, those would be software's constraints. Right? They're the equivalent of physical constraints in other engineering fields. I think it's a really good description of all the quality attributes that you might have in software. Right? It's a sign that we've matured as a field, and we can write these down and look and say, oh, that's pretty good, that's true. So let's look at it. So we have 9 attributes, 9 top-level attributes in the latest version of ISO 25010. Attribute number 1, functional suitability. Attribute number 2, security. Attribute number 3, performance efficiency. Number 4, maintainability. Number 5, compatibility. Number 6, safety. Number 7, reliability. Number 8, interaction capability. And finally, flexibility. So if you look, they then break it down into a variety of sub-attributes. Right? Each attribute is broken down into a bunch of sub-attributes. And if you look at this, right, most of these constraints defined for software engineering can apply equally well to physical systems as they do to software engineering. Right? So let's look at an example. If you have a house, the house is not functionally complete if it's missing a roof. Right? So this applies to software as well as it does to physical systems. If you look at a train is not interoperable if it's too big for the railway. If you have the rail tracks, the train's too big or too small, it's not interoperable. Okay, if you have a vehicle, it's not reliable if it won't turn on. Right, so that's another attribute here. If you have a laptop, it's not maintainable if I can't replace a cracked screen. Right? If you have an office building, it's not safe if it can't withstand an earthquake of a specific magnitude. Right? So I've given you a few examples where all these definitions from ISO 25010 were created for software, but they apply as much to physical systems as they do to software systems. Right? Now, you'll see the difference is that when I describe any of those attributes to a physical system, usually the constraint is a physical quantity, right? It's the laws of physics that's constraining it. Whereas if you look at, sorry, I'm going to turn it off now again. Go. If you look at a software system, none of these constraints are really bound by physics. Right? There's not a physical system that bounds things. Okay, go back. Okay, now you might say, aha, I got you though, right? You're thinking performance efficiency, those attributes here, right? So physical system performance efficiency might be something like vehicle's acceleration, the energy consumption of the vehicle, the passenger count, right? Those would apply to those 3 sub-attributes. And you might argue that a physical constraint appears in software systems. If you look at these 3 things, you could say those are physical constraints. Right? Now, certainly, when you write software, you have to consider resource usage in software systems. Right? There's only so much compute available, there's only so much memory, so much bandwidth, so much storage, and so on. And arguably, those derive from physical quantities. They're based on the hardware that you run on. But maybe this is the only place where software has to respect physical constraints, some law of physics somehow. But even here, in these cases, I don't think it's the case, right? Because when you write software, the reality is you can often substantially optimize software to meet these quality constraints. Or you can wait one generation of hardware for our hardware to completely obviate your constraints. Right? To completely obviate the need for optimization. When you write software and you realize you're constrained by one of these things, it's not really physics holding you back. You just have to work a bit harder to optimize most of the time, or you just wait a little bit, hardware gets faster, you don't have to do anything anymore. So physics wasn't really constraining, it was just a little impediment in your way. Okay, and we even have a term for this realization, that you can just software a bit harder or just wait a little bit and stuff gets better. Right? We have a term for this, bloatware. Again, we know what this is. Right? So if bloatware as a term exists, is that we've internalized as software developers that software is just kind of bloated. Right? We can just make it a bit better sometimes and it's fine. So I don't want to dismiss what seems like physical constraints on software, but there's an important realization to make here. Software has lived in a world of abundance. Right? So I'll give you a concrete example. If you're an airplane manufacturer, can you wait just 2 years for the speed of your airplane to double? That's not a thing, right? An airplane doesn't get faster every 2 years. Twice as fast every 2 years, that's not a thing, of course not. But software can do the moral equivalent of this. Right? Why can't an airplane get twice as fast every 2 years? Well, physics. At some point, you hit the speed of sound. Airplanes today, if you try to make it twice as fast, you hit the speed of sound. You pass it. You have to design a completely different airplane. Software, not so. You can wait 2 years, your processor gets twice as fast. And so software has physical constraints, but they're usually easily overcome. So rather than thinking of constraints, I would consider also the freedoms in software versus physical systems. Because I think considering the freedoms of software is also very important to understand the constraints and how we can work with them. So there's really three freedoms that I would attribute to software. Constraint number one would be that it's intangible. So by that I mean it doesn't have a physical form. I can't touch software, right? I can turn it off and on again, but the physical embodiment of it, the laptop, switch the power button. The software itself is intangible. It doesn't have a form. That's a really important realization. It's a freedom that software has that other engineering fields do not have. Number two, it's freely and accurately replicatable. I can copy software 1 million times over, and it's exactly the same. Right? It's very hard to copy any physical system with extreme accuracy. First, it's expensive to copy a physical system. And second, it won't be exactly the same. I have to put a significant amount of effort to make it the same. And third, software is remotely modifiable. You can modify software remotely. Right? I can't modify an airplane while it's flying in the air. I can modify its software, but not the airplane itself. Same thing for a car, same thing for a power plant. So I think these are the three really important freedoms that software has compared to physical systems. And so when you combine those freedoms with the constraints that software has, you really get a design space and you get to understand how can I create engineering? How can I tune the concept of engineering towards software? Okay, so there's very interesting implications for this. If you look at the freedom, well, what it means is I can virtually test and verify software very easily, virtually. And if you remember the software crisis, they wanted to do simulation. That's totally doable. I can have a high development cost, but really low distribution costs. Distributing software is really easy. I don't need to go on the shelves of a store anymore to distribute software. I can just do it over the internet. Very cheap. The cost to develop is high. The cost to distribute is low. That's not the case for other engineering fields. A car is expensive to make. Every single car. An airplane is expensive to make. Every single airplane. You can easily upgrade or obsolete software. Now, it has an impact when you upgrade obsolete software, an impact on the consumer, an impact on the ecosystem, but it's easy to do in software. It doesn't mean that you should do it, but it's easy. And finally, software is really scalable. There's issues that scale in software, right? It's not easy, but you can distribute that software in a bunch of different machines and then scale it very easily. Okay, so as we discussed, hardware resources that support software are currently improving significantly over time. So what's called Moore's Law, right, has the number of circuits doubling every 2 years. Now people are saying, oh, Moore's Law is dead, it's not as powerful as before, it's slowing down. Maybe, but hardware still gets significantly faster. If you look at the number of, say, floating point operations per second that machines can do today compared to what they could do 2 years ago, it's grown by much more than 2x. So software is living in a world of abundance. And this abundance has been the biggest freedom afforded to software. So what I just outlined might sound obvious, but it has non-obvious impact on software quality. For example, when a customer buys a vehicle, they don't usually think about the factory that made the vehicle. When you buy a car or an airplane, whatever, you don't think back to the factory that made it. However, automakers put a lot of effort into the factory, a lot of thought into it. So the Toyota production system, for example, improved the quality and decreased the cost of the vehicle significantly, which means the factory is a big investment in making really high quality products in a physical system. So what's the production system for software? Well, it's the collection of software, tools, and processes used to produce software. Software produces software just like machines produce machines. However, a real factory is tangible, it has variance, and it can't be used forever at any time of day. Right? You have to have humans involved in this. So an intangible software factory should be operable 24/7 in perpetuity. I should be able to build and test all software components together upon every software change for each variant of the end product. So remember, simulation and testing were two of the solutions identified for the software crisis. So what I'm saying is not wrong. Right? And so, given that I should be able to do this in the virtual software factory for the end product, right, the end result that will be delivered to humans, then who here in this room has fully automated builds, testing, integration, and deployment? And I don't mean of your little system, right, but of the bigger system that ships to a customer, like the final product. Right? Do we create products that are fully automated, built, and tested for the whole production of the software that goes into the final product? Right? Similarly, software is really and accurately replicatable. So it should therefore be completely hermetic and reproducible. Right? So what I mean by that is it should require no external input to build and produce the same output every time. I should be able to take a box, put software source code onto it, unplug the internet, build the code, and then have the same binary come out every single time. I should be able to do this on many boxes. I shouldn't be able to, I shouldn't have to pull things from the internet afterwards. So who here produces software that's completely hermetic and reproducible? Same thing, software is intangible, so I should be able to know every single piece of software that went into producing the final binary. Right? So not only the source of the end product, but all the source for the tools that went into it, the libraries, compilers, all the tool chain, and so on. Do we have comprehensive bills of materials for this? I don't think so right now. Like we have SVDX Lite, which is helping us get there, but we don't really have this today. Let me turn it off and on again. You know it's not a scripted joke because it's getting really old. Okay, so given that, I'll give you an example. So software is modifiable remotely. Right? It's testable, verifiable virtually. I should be able to update my software over the air, including updating the tools used to build said software. That doesn't sound like magic, right? Being able to do over-the-air updates seems like something I should be able to do based on what I described. So recently, NASA updated Voyager 1. Voyager 1 is 24 billion kilometers away from Earth. 22.5 hours away thanks to the speed of light, right? When you send a message from Earth to Voyager 1, it takes 22.5 hours to get there because of the speed of light. The speed of light is really, really slow. But imagine that. This system, Voyager 1, is a 46-year-old system, and NASA was able to update it remotely, like last month or something like that. That's pretty amazing. Right? That's nice. It's not really over-the-air update once we get into space, but it's still pretty amazing. So, can we update software easily? Right? Now, I understand if you say, well, I can't update my software easily because of the speed of light, like the round trip time is two days. But Voyager 1 is the furthest system humans have from Earth. Right? And single round trip is 2 days. Can we easily update any software we create today? Not just the software, but all the tools that we use to generate that software, and then update the final consumer product, knowing that we don't degrade the quality of the software. Right? What I've outlined here, I think, are some of the systems of it, the symptoms of issues that make it hard to realize a software-defined vehicle. Right? There's symptoms, but what's the root cause? So I think that we haven't embraced the constraints and freedoms of software. And why is that? Well, it's because software is a new field, maybe it has, but it's not really because software is a new field. It's because software has evolved expertise, standards, and regulations fairly rapidly. Right? Over a lifetime, we've evolved all these things. We're adding new things. We have safe, we have agile, we have DevOps, we have this, we have that. It's changing all the time. So let's look at the timeline again. In here, there's entire industries and sub-professions that have been created in the last just 2 decades. Right? Scrum Masters weren't a thing 2 decades ago, they're a thing now. So as we cope with software, we've accreted expertise and standards on top of each other. We have all these things piled on top of each other. And this accretion creates overhead, right? So the youth of software engineering is not a reason to say we don't engineer yet, but the rapid accretion of practices might be one of the reasons that we don't engineer. So the actual speed of light is this number in a vacuum. So to realize software-defined vehicles, I think we have to embrace the constraints imposed by software on the system. We have to understand the moral equivalent of the speed of light for each of the constraints. If you look at the ISO 25010 quality attributes, each of those has the equivalent of this is the speed of light, this is the fastest you can go ever, right? And you have to understand what that is and where your current system falls in that range of the speed of light. Right? And so for each constraint, what's that speed of light? So in software, what's the most compatible that software can be? What's the most reliable system? What's the most reusable system? And when I say this, I don't mean measure the quality of the individual part, where I have this part of software, that one, that one. I mean measure the quality attributes for the whole product, the end product that the consumer experiences, right? Because what we want to do is we want to measure the outcome of the entire system on humans. Okay, so let's look at what our industry aspires to, software-defined vehicle. What's the biggest impediment that we have not shed? An impediment that causes significant trade-offs in the design of software, in its reuse, and how fast we can deliver software and what quality of software is achieved. There's a hint in the name, software-defined vehicle. What's the biggest impediment for software-defined vehicles? I think that's the biggest impediment, it's hardware. Right? The shadow on top of SDV is hardware. Why is that? Well, the tool chains we use, the standards we follow, the libraries we have access to, all of these software concepts are limited by the target hardware. The board support package, the operating system, the compilers are all tied to the hardware. The mechanisms for communication inside an ECU to other ECUs, the boundaries of software components are all determined by hardware. The accelerators you have available to you, how much computation can go into an ADAS pipeline, the extensions available to the platform, including an AutoSAR, defined by the hardware. Right? All of these are determined by the hardware. So hardware is an artificial constraint. And when you build an automotive system, the first thing you pick is the hardware. Right? So if the first thing you pick when you design a vehicle is hardware, and that hardware determines the software you get to use, then you have a hardware-defined vehicle. And so the hardware vendors choose how the software that executes on the platform, how it's offered. The hardware determines many of the technical constraints. Chiplets, they're kind of the hot new solutions these days, chiplets, for some of these problems, but I like them, but they won't fix most of the issues I've outlined. Okay, so how can I reuse code when the tool chains and standards I can use change only when I change hardware? So have you tried updating a compiler after more than 3 years without updates? What happens when you try to update a compiler after developing a bunch of software, and then 3 years later you try to update the compiler, is that it'll find a variety of miscompiles and behavior changes. Compile time regressions, code regressions, runtime regressions. And many in the industry, what they do when this happens is they just copy the code over and start from scratch. Right? You start the software from scratch rather than being able to invest in its quality over time. So we go back to the Google definition of software engineering. They claim it's programming integrated over time, but I think that's really technical debt. If you do software engineering integrated over time, you get technical debt out of it. You have near zero quality and mostly debt. So, can we maintain a bunch of software versions? So imagine this is your source control, and you do forks of forks of forks to be able to ship multiple products. Is that maintainable? Right? Imagine you have hundreds of variants of software in your product that you ship every year, each with their own different non-reusable code base using different hardware. There's no way you can maintain this and do over-the-air updates over the lifetime of the product that goes into consumers' hands. Right? Software-based configuration management for the entire end product is not sufficiently common to contain this type of complexity. This is a very simple dependency graph here. Okay, so here's the classic layer diagram. You'll see a lot of them this week. Each with their own set of software tools. Each of these boxes in an imaginary layer diagram have different software tools. How many operating systems are in a single vehicle in that layer diagram? How many TLS, transport layer security libraries, to encrypt communication through Ethernet and wirelessly would be in that diagram? How many different types of tool chains are used to compile vehicle software? How many different programming languages and standards and versions and so on are in that layer diagram. That layer diagram is what you find in every vehicle, and each of these boxes is actually kind of more like that. They're all little ecosystems that have their own set of solutions that determine the software you can write, and the reasons they're different, the reason the software is different, is because of the hardware that's there. Now, sometimes there's good reason to do that. Maybe you have safety versus non-safety systems, you have some amount of duplication, but fundamentally, most of the redundancy in software choice is driven by hardware. And the end product, the vehicle you get, contains the multiple versions of the same functionality based on decisions by the ECU parts supplier, the board support board, and so on. So here too, I don't think we're embracing what makes software unique. We can have software parts from multiple sources which nonetheless interface with each other. Each of those boxes could share a lot of stuff, but because they're tied to the hardware and the hardware manufacturer decides what software you use, they don't share that much. There's some things they share, but not a lot. Right? And sometimes there's a perceived tension with safety. Right? The industry, following ISO 26262, has settled on a process that helps developers create safe products. That's really good. Safety is really important. But how we do this is we freeze software, we freeze tooling, we freeze resources, we avoid changes. That helps create some amount of quality, because safety is really a top priority, but we have to realize that preventing change in software is not sustainable. If we freeze everything and then 3 years later we try to update it, that doesn't give us a software product we can invest in the quality of. Right? So what we've done instead is we've imitated the constraints that we put upon physical systems, upon the hardware. We imitate the hardware constraints in software. And even then, that's not fully true, right? Because can you imagine a factory that produces cars that never changes? Right? When you create a factory, that factory changes. When you create software, the software factory right now does not change, except it keeps having bugs. Right? And the core of the Toyota production system is Kaizen, right? Continuous improvement. And continuous improvement in factories means that the factory updates daily. Every day the factory changes. Yet our software factory, our equivalent of that, improves only when the hardware changes. So fundamentally, I've been describing a hardware-defined vehicle. So I'm not saying that hardware is not important. It's really important. You need good hardware. Like very few people do pen and paper execution of software. You can't run software without the hardware. But what I'm saying is that to realize a software-defined vehicle, we have to use the constraints and freedoms that make up software, and we have to do so with a focus on the end product the consumers purchase, not on the individual parts. And I think the individual parts create artificial constraints on how we create software. Those are not real constraints, right? They're not the equivalent of physics for us. Hardware is not a real constraint because the hardware manufacturer choosing the software you can write means you have a hardware-defined vehicle. So in conclusion, to achieve software-defined vehicles, I've got 3 recommendations. First, we need to embrace software's unique constraints and freedoms. Second, we have to focus on the entire system's quality as the consumer experiences it, not our individual parts. And third, we have to move from crafting to truly engineering software. That would be for the benefit of the users and the advancement of our industry and for society. So with that, thank you.
Thank you, Mr. Bastien, for your excellent speech. I think I can allow for 1 or 2 questions to you. Are there any questions in the room? I currently don't see one, but I have one. You mentioned the safety and reliability issues, even for software, as far as I know from my background. The measuring of reliability and safety for hardware is much easier than for software. Yes. How do you see the progress in this field?
In software and hardware?
Software.
In software. Well, I think the way ASIC's decomposition works is really powerful, right? I don't think that the tools we have, though, are particularly well integrated to do safety. If you look, most software in safety systems is written in Ada, C, or C++, with a variety of standards on top of it, such as MISRA. There's And those are layered on top of each other, right? If you look at the earlier NISRA, a lot of NISRA was very well intended, but was not integrated with the tools that they were applying to. And so a lot of NISRA, and I'm not picking on NISRA, we have people who've been working with NISRA to improve it, but I think the original NISRA was not automatable and as usable as it could be. It wasn't embracing what software could be. And I think that's true of other fields as well, where we look at a tool, right? We look at C and C++ and we say, well, that's got a lot of sharp edges. Let me try to make it not sharp. And I think you end up with layers rather than a system that works well together. So, for example, in C++, and again, this is just one example, in C++, we're trying to improve the safety and security of the language. On July 12th, so in 2 days, because we're in Japan, there's going to be an announcement of a safety critical Rust, so Rust programming language, to try to create an environment for safety in programming languages. And I think this is just looking at programming languages and the standards to use it. I think all the layers of software can do that. I also think hardware is not really utilized sufficiently to create safety. A lot of the hardware that you find in vehicles today, the microcontrollers are pretty good, right? They have a lot of redundancy things, but a lot of the more powerful hardware is 5-year-old smartphones that you then tune to be able to use inside of the vehicle. And I think that's a source of issues because that's a general compute platform that's not necessarily well suited for this type of software we're trying to write. So I think closer hardware-software co-design would help mitigate these issues. So I think if you look at the whole layer from the application to services, to middleware, to operating system, to hardware, there's a lot of opportunities to collaborate across these, cut through the layers, while everyone still has a viable business in their layers. You can cut through the layers and create a safer and more high-quality system.
Well, thank you very much. I don't see any further question now. I see one over there.
My name is Anton Kushnir from the company. Really sorry, maybe I missed it. You mentioned two terms, crafting and engineering of software. First of all, first part of the question, could you please give short definitions of this?
Yes, so I had a definition of engineering at the beginning. I did not have a definition of craftsmanship. I think crafting is something that you end up having an apprenticeship system for, right? So you'll have a craft master who's really good at this specific craft, who's recognized by the community or something like that, but they're very unique when you're a craftsperson. And then there's usually an apprenticeship system where the aspiring journeyman or apprentice gets to evolve their skills under the master's guidance to become a crafts person. I think a lot of software development is craft. I've worked with excellent software developers who are wonderful craftspeople, but they're very rare, and we all aspire to be as good as they are in what they do. Right? And I think engineering would be a practice where you have formal training and then you work under particular engineers for a while. But it's much more scalable and reproducible, right? Where you don't have to have a craft person, a few craft people lead it. You can have an entire body. So when I used to work on airplanes, I interned on business jets for a big airplane company, and I did mechanical engineering design. I was not an engineer back then. I was not allowed to do an AutoCAD drawing or something like that that would ship to the vehicle without being checked by someone else. I was able to do that work. I was still in college, and I designed things that go into airplanes. I was not the one signing off my name on it. Right? And so I think there's a big difference between craft and engineering, where there's a whole system of responsibility towards what you do. Like any drawing that I did had to go through weights validation, fire safety, through physical systems check and so on, before it could go into a real airplane. And I think that's the big difference between craft and engineering. Engineering is much more scalable, much more reproducible, and creates quality at scale, whereas craftsmanship creates really high quality, beautiful things that there's just one of. Right? So if you think of really well-crafted software, there's really, really well-crafted software, not necessarily high quality, but there's really a lot of beautifully well-crafted software. It's not engineering.
So thank you, Mr. Bastien, for your presentation. We come to the next topic.